time to start. So today we'll talk about, first I'll introduce myself. My name is Kai. So this week there is off campus for a conference. So I will give lectures for today and Tuesday. I'm not a very professional machine learning guy, but at least I know all these basic things. So if you have very detailed questions or some good questions, if I cannot answer, it's fine. We can save the questions, and we also have colleagues that we can discuss it. So if you have any questions when I'm talking the lectures, you can just and ask the questions. Okay, so today we'll talk about multi-node and multi-layer neural network. So I believe last lecture you've already learned about neural network of only single node. So let's first review about it. So for example, we have a picture like this, and this picture is presented by pixels by pixels. So each pixel is a number, right? So like this row have x0, x1, x10, and so if we put it into a neural network architecture, it is actually a weighted sum. So you put sum over x0 times w1, w0, x1 times w1. So each w is a weighting for each pixel, and then you use the activation function to squash it, and finally get a number, which is we call it this classification result. Okay, so instead of one node, in the real neural network architecture, we can have more than one node. It can be several nodes. So it is the same. Like it's kind of, you do the same thing, weight the sum and squash it several times. The only difference is for each node here you have different sets of weights. And okay, so this is the outline of today's lecture. We have first we go through neural network for the modeling propagation with multi-layers, and then we go through back propagation, and then I'll show you a MATLAB example, very simple, and we'll go through summary. So first, let's look at multi-node layer neural network. So if you look at here, this is a multiplication of matrix. So it's quite simple. x1, x2, x3. It's that means the value of pixels. And here we have two sets of weights, and you do the multiplication, you get two numbers. So it's two classification results. This is a diagram, and then you put a function in it. We usually call it the activation function. Then we get the result. So here we call. You can see here we have several layers. So layer 1, layer 2, layer 3. So the node in each layer we put the notation here. So we call it A1, which means it's the node in the first layer. So it's the representation, we already talked about it. It's the weighted sum, and then you put a activation function in it. And then you use the result in the first layer, you use them as input, and then you calculate the second layer and the third layer, and so on. So this is a notation. Here Z, we call it the weighted sum of certain nodes, and we put activation function at Z, which is the output of the weighted sum. and we get final value in a certain node. And this is a very, kind of typical representation of L2 norm. So you calculate the L2 difference between the predict data here and observed data. Of course, you can add a regularization term. So this, you see, I think most of you see it a lot in most of the inversion problem. So, yeah. And this is very simple code for the inversion. This is a steepest descent method. So you calculate the gradient, and you update W with gradient in each iteration. Okay, I think this is quite a simple concept. Any questions?
I have a question.
Yeah.
In one node system only, for example, the one that's
Okay.
here,
Yeah.
we know T1 and T2 already, or in this case A1 and A2 already. We want to train our network to get T1 and T2. That is our result already, Y values. In multi-layer, do we already know these A1 and A2 and A3 stuff?
No, we don't know.
So we calculate it, and the
Yes,
final
we
result.
calculate it. So when we in the training stage, we have the output
Yes.
and we have this input, but inside we don't know. We are training the weights, and the weights will give you the result of A1, A2, A3. It's the same, right? So the weights is what we are looking for. Once you have the weights, you use this this algorithm. You can calculate A1, A2, A3, right? Okay, so this is we talk about some details of for the propagation. So here we have multi-layers, but it's straightforward. It's like we calculated layer one by one. So we first calculate the first layer. We use A0, which is our input, and you matrix multiplication with the weighting matrix W, and you add the activation function. So then you get the first layer, and then use the first layer result to calculate the second layer, the third layer, as we just talked about it. So it's straightforward, just go like this. And this is the MATLAB code. So Z is the sum, the weighted sum, right? And A is after you calculate the activation function. And then you do the iterations by different layers. And this also is another way of express what I just talked about. It's quite
Excuse me, sorry.
Yeah.
Can you go back to last slide?
Sure.
I wonder why you use a 3D array. I mean, the W is a 3D array, right? In your pseudocode.
3 array.
Yeah, it's a three-dimensional
Yeah,
array.
yeah. So W, they're K is the layers. I'm not quite sure. It should be 2 dimensional.
Okay.
Yeah, 2 dimensional. Yeah, it should be 2 dimensional. Okay, so this is, I think, we just talked about. Yeah. This is just to go over through it again. So I can go through it again, so we can see, we calculate x1, x1. x1 to x3 is the input. We calculate to get a1 to a3, and then we replace a1 to a3, put it here, use the input for the next layer, for the a1 to a3 here, and then we get the new result, and then the activation function to give the result for first layer. Yeah, it's just some, just same thing. Second layer. Yeah, it's just an illustration of this, the whole procedure.
Okay.
Is it clear for the poly? So let's go. This is summarizing. Yeah. So the difference with A and B is that in B we have a bias term B. So we have bias term here. So at first we just talk about like inputs and weights, and now we add a bias term. And this is code. Okay, so question, what if you want a wide range of output numbers? Anyone can answer this question? I think if you want to get a wide range of output numbers, then it's a matter of the activation function, because the weighted sum is done, and then it depends on your question. People usually want to make the output to be more distinguishable, like, because we do classification, we want like it to be 1 or 0. It's you don't want a lot of numbers between like 0.4, 0.6. You want it close to 1 or either close to 0. Then it's a problem of activation function. We'll talk about later. We can use some other activation function. Or yeah. Okay, so then we'll talk about neural network backpropagation. So first, let's recall the previous lectures. I think you already learned the theory of inversion problem, right? You've learned the steepest descent method. So if we look at this formula, we have K, which is the weights in the case iteration, and it should be K plus 1. Okay, and then we have previous weights in the previous iteration, and this guy is the gradient. So this the steepest descent method. We update the result using the gradient, and then alpha is the step length, or in machine learning sometimes we call it learning rate. The same thing. Okay, so next is problem is how can we derive such a gradient, especially in you have a multi-nodes and multi-layers. Okay, so it could be a little bit tricky. So this is we already have the full propagation formula, and this is the diagram. What we can do is let's first do some notation. Okay, Z1, Z2, and Z3 stand for the output in each layer.